Welcome to Brain Vision.
Okay, so we have quite the setup in this problem. So we have a coaxial cable, and so in this middle part of it, there's three distinct regions. In this middle part, we have current going one direction with total current I naught. Then we have an insulating layer, the black here, and this outer blue region, we have current going in the opposite direction of total current negative I naught. And then we have the region outside the cable. And so in these three distinct regions then, the middle red, the insulating black, the outer blue with current going the other direction, and then just outside of the cable. In all of those regions, we want to find what the magnetic field is. So the inner part of the cable has a radius R1, and then the black part R2, and then the outer part R3. And then I'm calling our position anywhere within the cable just a lowercase r. And we know then we have a non-uniform current density in these different regions. So in the middle here, our current density J1 is just equal to some constant C1 times R, wherever we are in that, so it increases linearly. And then a little confusingly, we call J2 the current density in region 3. So the black region just has no current density. And then J2 now corresponds to the blue current density. So same thing here, some different constant C2, and then the current density just linearly increases with R. A difference is, though, that while the inner red part will start with a current density of 0, because R can be 0 there, in the blue region, R is going to start at value R2 and then go out to value R3. So we'll get different kind of distributions here. So to start, we want to find what these constants C1 and C2 are, since we can't give our answer in terms of those. And once we have those constants, then we'll look at finding the magnetic field in these four regions. So to do this, we can say that our total current, so let's start with C1 here. So in region 1, in the middle of the cable, we know we have total current I naught. And we know that has to just be equal to the integral of the current density over the cross-sectional area of this. So current density is just current per area. So if we integrate current with respect to dA around this red region, we should have our total current, which is I naught. So we're just integrating J dA. And so we'll set up our integral like this. We'll have infinitesimal rings. So these rings will be a distance r prime from the center. So r prime, I'll say, is our variable within the integral, and then just regular r is our position within the cable itself. So we have some distance r prime from the center, and then this has a thickness then of dr. And so this total infinitesimal area is dA. And so that would then equal 2 pi r prime. So this circumference times dr. And I guess we should really call this dr prime. So we substitute that in for our integral. So we're integrating from all of region 1. So from 0 out to R1, so the middle right here, all the way out there. And so we can substitute in for J, so that's just this constant C1, and then it's times R, and I'm again going to write this as R prime, since we're referring to the variable of wherever we are within our integral. So C R prime, this is RJ, and then dA of 2 pi r prime for the circumference, and then times dr for the width. So that's our dA. And so we can write that. It looks like we would have the integral out to R1 of 2 pi C1, and then we'd have an r prime squared dr prime. And so that should come out to be 2/3 pi r1 cubed times c1. So I kind of skipped a step here. So we were just evaluating this from 0 out to r1. But when we substitute in 0, we get nothing. So originally this was an r prime, and we were evaluating from these limits. And then we get this then for the integral. And so now we just have I equals 2/3 pi r1 cubed c1, and we can solve for c1. And we should get that is equal to 3 I naught over 2 pi r1 cubed. So there's C1. C2 we'd set up in the exact same way. There's nothing different about this except the limits of integration. Now we're going from this point here out to this point. So we're integrating from R2 out to R3. And so now we would have this whole expression, but it would be R3 cubed and then minus 2/3 pi C1 R2 cubed. And so when we go through with that and solve for C1, we're just doing the exact same process. We should get negative 3 I naughts. So also we replaced I naught with negative I naught here, since the current's in the opposite direction in the blue region. So negative 3 I naughts over 2 pi, and now it'll be R3 cubed, and then we'll get a minus R2 cubed down there as well. So now we have our constants C1 and C2. And so now we can go about finding what the actual field values will be in these places. So we're just going to use Ampere's law for that. So we'll go on a new page here, and we'll start with region 1. So that's the red core, so from r equals 0 out to r equals 1. And so Ampere's law is just B dot ds, and that should equal mu naught times the enclosed current. Well, B dot ds here is easy. That's just going to be the magnetic field, which is what we want. And then when we do the integral of ds, so we can pull B out of the integral here because we know it's going to be circularly symmetric. So we're really just integrating ds around the loop. And so we're going to be at a given point, and we've called that point little r. So we're at some point little r in this red core, and we want to find the magnetic. So we integrate around that path. We should just get the circumference 2 pi times the little r. So we have B, which is constant because we're radially symmetric here. So 2 pi, and then little r, and then B, and that equals mu naught times I enclosed. But I enclosed is a little bit harder because we aren't necessarily covering the full red region. We could be anywhere in the middle, and so we have to set that up as an integral. So we need to go from the middle out to wherever that part is, out to little r, and then we need to integrate just our current density. So just like we did before, JDA, to find what the total enclosed current is. So that's mu naught, that integral, and then J we know is just C1 times R. So we found C1, but I'm going to leave it just as a constant for now, so I don't have to write all of that down. So our integral variable, we integrate with respect to R prime is how we've set it up. So the limit of our integration is whatever point we happen to be interested in the magnetic field here, so out to some point, and then we integrate with respect to R prime out through this whole region until we get there and find the total enclosed current. And just like before, then we have our current density, so that's J, and then dA will be 2 pi R prime dr, so just the integral of one of those infinitesimal rings. So now we have 2 pi r b, and when we evaluate this integral, we should get mu naught, and then we'll have 2/3 C1 r cubed, and I think we probably have a pi in there as well. So we just have some constants, then we're integrating r prime squared. And then we evaluate that from 0 to r. So whoops, this should actually be a little r cubed. So to whatever distance out we are going. And we're pretty much set now, so we just want to solve for b now. And so notice that this depends on r as well as that, so we're going to get a more interesting result. And so we should get mu naught I times pi, and then we have r cubed over pi r1 cubed. Yeah, so that's substituting in our constant of c now. So all I did was substitute in c, and then we divide by this 2 pi r here. And, oh, I think we missed that. Actually, we still have our 2 pi here times r, sorry. So then we finally fully evaluate that, and we should get b equals mu naught I r squared over 2 pi r1 cubed. Sorry about that. So first we were just substituting in for c, and then we solve for b here, and so we had our r's cancel out. And once again, I keep writing this as capital R, so that is little r as I've been writing it. So our magnetic field then is the position we're at squared, and then the total radius of the inner region cubed on the bottom. So there's region 1. Going on to region 2 now. So here we have, again, integral of b dot ds, but that we know is just going to be b times 2 pi r. It's always just going to be that. And then mu naught I enclosed. Well, now we're in this black region. The black region contains no current, and so we know the total current enclosed always just has to be the total current in the red region, and we know that's I naught. So this one, we're kind of catching a break here a little bit. So that should just be mu naught. Really, this is I enclosed, and now it's mu naught, just I naught. And so we can solve for b then pretty easily, and it's just mu naught I over 2 pi r. So here we just have our current decreasing over the whole, or our magnetic field decreasing over the whole region, since we're just getting farther away from current. Now in region 3, so now we're moving out into the blue region, so we always are enclosing this current I naught, and now we're going to be enclosing more current, negative current this time. So same thing, the integral of b dot ds is going to be b 2 pi r. And now we have mu naught I enclosed, and our I enclosed, we know we're always enclosing the red region, so we always are going to just have I naught. And then just like before, to find the amount, the new current, the negative current now, they'll be enclosed in the red region, or in the blue region, the outer region. We need to integrate, and so we integrate from the start of that region, R2. So really we'd be integrating from R1 right here, but I know there's no current from R1 to R2, so it's going to give us 0. So we can just integrate from R2 out to whatever point we happen to be at in the blue. So from R2 out to whatever point R we happen to be at, and we do JDA to find the current enclosed, so C2 times R, and then we integrate this with R prime as we've been doing, and so 2 pi R prime again, dr prime. And we can evaluate this, so we'll have mu naught I plus, we should have mu naught, and we will have now minus 2/3 pi C2 and little r cubed minus r cubed, r2 cubed. So I'm skipping this integral because it's very similar to the one we just did over here. So we're doing the exact same thing, integrating JDA. And instead of 0 to R, we do from R2 out to R. And now we can start simplifying this a little bit. So we substitute in for C2, and we should get mu naught times I minus mu naught. And then C2 has a bunch of R's in the denominator. Oops, I think that should be a capital R. Hard to keep track of all those. So we'll have R cubed minus R2 cubed over R3 cubed minus R2 cubed. So all these in the bottom are coming from our constant C. But this now is our magnetic field in region 3. And region 4, thankfully we won't need much space for. So just like when we were looking at region 2, the black, and we knew exactly how much current contained, well, whenever we're somewhere out here outside of the cable, I know exactly how much current we contain because the red region has current I naught and the blue region has current negative I naught. So our total current is 0. So B times 2 pi R just needs to equal 0. So only way that works is if B is 0. So outside the cable, the magnetic field is just 0 everywhere in region 4.